Thank you very much for the kind invitation to this workshop. I had kind of quick difficulties while preparing this talk because it is actually a promotional talk. So I'm advertising a book project that we are about to finish with co-authors Tanja and Balin, who are sitting just in the back, and R.Nagel. And so this talk is more or less a promotional talk that you all should buy this book. When it appears, and I hope, so we are now in good hope that it appears soon. But the problem is which community to address. Do I address the functional analysts, the operator theorists? Do I address the ergodic theorists? Now, since I'm myself from functional-analytic background, I'm actually a newcomer to ergodic theory, although I learned this now for several years, but I'm still feeling myself as a newcomer. So my goal with this talk and with the learning of ergodic theory is to spot the functional analytic aspects of ergodic theory and actually reformulate a lot of existing ergodic theory in a purely functional analytic way, when it's possible, of course. And in this way, trying to lure other functional analysts into that area, so who may be abhorred by some very combinatorial arguments and whatever, where they could be abhorred by. But so to make that it's operator theory, and so I hope that other people join and also see ergodic theory as an actual field of an application of functional analysis. So this is the background. My goal now for the next 10 minutes is to explain the main thrust of our approach to ergodic theory, which of course is an old approach. But the difference is that, well, at least from my side, I want to apply this approach quite consequently. So quite determined to follow this approach and not switch to other approaches. Which of course can also be an obstacle, but it could also be quite interesting whether such an approach is possible. Okay, so here is a bit of setting the stage. So maybe I need this, well, I don't know. So this is my first section. I am writing usually a capital X for a probability space, and if the measure is actually mentioned, I would just call it mu X, because everything is like the probability space is the underlying object, and it has a state space, a sigma algebra, and a probability measure. And of course there's a measure-preserving transformation, so measurable and preserves the probability measure. And from this setting, one derives an operator. That's the Koopman operator. Usually, I abbreviate this just with T. So T is the generic symbol for a Koopman operator. T is T phi, which this is just the composition operator in Wolfgang Arendt's language. On X. Now, this is an operator that maps L1 of X to itself. Also, it maps LP of X to itself and L infinity to itself, and has a nice, has a lot of properties. For example, so it preserves, of course, the one function, and it preserves absolute values, just because everything is defined pointwise, and it preserves the integral. So that it preserves the integral is just that phi is measure preserving. So this is the measurable setting. So I usually take the notation for that, let's say x phi. So x is identified with the whole probability space. In LaTeX, I would make a difference in the notation here at the board. It's a bit difficult, but I think you will get it. So this is the measure-preserving situation. Of course, there's a topological analog. That's the topological dynamics, and I'm introducing this too. So this is the other interesting case. So you have a compact space, and you have a continuous map here, and then we denote this by this pair k phi, and then you also have the Koopman operator here, and that works on continuous functions in the same way. So Tf is f after phi. Now, one of the first decisions that we had to make in the book, and which comes from our actually background from semigroup theory, is that we do not restrict to invertible transformation. So we see semigroups everywhere, and groups are, of course, special cases, important special cases of semigroups, but we are interested in whether one can do theory just without an invertibility assumption. So this is, so let me put this here. That's kind of our EFHN philosophy, where I'm a bit patronizing here. Maybe it's just my philosophy, but so I tried to enforce that in the book, and I think Rainer was also in favor. And you can ask my two co-authors whether they actually liked it or not. So one of the first decisions is that we do not restrict to invertible systems. So non-invertible systems is so where possible or where reasonable, of course. So just looking at which theory can be done there. So okay. So the next point, so that's the, these are the objects of study. Now, the next observation here is actually, it's about, so in ergodic theory on topological dynamics, very often one would restrict to metric compact spaces, metrizable compact spaces, or to probability spaces where the sigma algebra is countably generated, or essentially countably generated. So we do not make this restriction. So my question is also in developing the theory, what can be said about non-metrizable case for non-metrizable compact spaces, or for non-separable, so to speak, probability spaces? So actually, a non-separable X, which is by which I mean actually that the L1 space is separable, but I will come to this later. Now the next important topic is what is an isomorphism, or actually a homomorphism. And how do I see this notion as a functional analyst? Now, in passing from probability spaces to the operators, we change the category, so to speak. So there's a change of category here. Namely the change, so one passes from measure-preserving system to the L1 space, or the L2 space if you like, and the operator. Now there's a natural notion of so actually, no, okay, the first thing to remark is that there is a natural notion of homomorphism here which is not present here, because here one has much more structure, linear structure. And so so I introduced the following class of operators, which has no direct analog on the state space level. That's what we call a Markov operator. So suppose X and Y are probability spaces, and so T, an operator from L of X, L1 of X to L1 of Y, is Markov. And so actually one maybe bi-Markov or bi-stochastic would be more appropriate, but somehow the terminology is borrowed from Glasner's, from Eli Glasner's book. He uses also the term Markov operators, and we thought we should not deviate from a standard textbook, standard book on that monograph and that topic. So is Markov, if T is a positive operator, that means it maps positive functions to positive functions. It is integral preserving, and it preserves the constant one function. So that's a Markov operator. So the Markov operators form, of course, a convex set, is closed in the weak operator topology. That's a Markov operator, and we call T a Markov embedding. So T is a Markov embedding, and usually I would only say M embedding. If it is actually if it's isometric, which is actually equivalent in this case to being a lattice homomorphism, that means it preserves absolute values. So this is actually the same as to say that TF1 is F1. So for all F, I mean everything is quantified for all F, you know. But that's not so important. So this is the important property here. Now then we see that actually, so the change of category goes to the pairs L1 of X with T being a Markov embedding, and now we can say what a homomorphism of dynamical systems should be. So the classical base space notion is that of a factor. So what is a factor? So classical, we would have a mapping tau of let's say one probability space to the other measurable, measure preserving and that's a factor if it commutes with the dynamic. So that means that so I write phi x for the dynamics on x and phi y for the dynamics on y. So this is the classical notion of a factor. Now a factor, of course, when we Koopmanize it, that means when we pass to the Koopman operators of this underlying map tau, then we arrive at a mapping S which maps L1 of y to L1 of x, and that's actually a Markov embedding because it's a Koopman operator, and of course it satisfies the commutation property. So the Tx here, so this is intertwines the two Koopman operators. Okay, so factors are in one-one correspondence. So you can okay, I'll write that here. And that also factors are in one correspondence. Okay, now before I say this, I should now underpin what's now the difference. I mean, when we are working in this category, we would apply this notion of a factor, but when we apply in this category, we would apply that notion of a factor, and that is not linked to that actually S is a Koopman operator of an underlying map. We're just saying, okay, if we have a Markov embedding into another probability space and satisfying this would be, then we would call L1 of y, well, y would be a factor of x. So, so this is already like generalizing the notion of a factor here, and now in a second I will show you how general that actually is. So in this sense of a factor, that means in this operator-theoretic sense of a factor, we have the following characterization. The factors are a 1-1 are in 1-1 correspondence with either of the following class. So the closed T-invariant Banach sublattices of L1. The factors of a system are in 1-1 correspondence with the closed T-invariant Banach sublattices of L1 that include the constant 1 function. So take a Banach sublattice of an L1 that is contains the constants, then it's actually L1 of a subsigma algebra, if you like. Okay, and because of this correspondence, also with the so-called Markov projections. So that's Markov operators that are projections. The square is the same. It's the operator Markov projections P on L1, such that well, the range of P is invariant. The range of P is a closed Banach sublattice containing 1, and it should be T invariant. So the T invariance is this operator-theoretic equality. So both collections of objects are in one correspondence with factors. Now, Sophie, please turn on the beamer. So I am trying now. I now ask the question: how actually? What do we lose here? Do we lose? Are we more general here actually on that side? And the first theorem here to state is now okay. 30 seconds. I have to talk another 30 seconds. So the first theorem to state here is saying the compact case. So when you actually when you you're not in measurable dynamics but in topological dynamics, you pass from a topological dynamic system to the CK dynamics, you don't lose anything. So you can go back and forth, it's just the same. So here the two categories are isomorphic. So now the picture comes maybe. Yeah, let's say there comes something, but not a picture, which it should come. So the beamer is on, but okay. So in the I'm summarizing what I will show you in a second on the slide. Oh, here it is. Oh, wonderful. Okay. So the first theorem here is actually classical theorem. It's in our book mostly, but it's of course copied from, like, for example, Schäfer's book. So if you have two compact spaces and you have a linear operator that preserves 1, then all these 4 statements here are equivalent. So T is multiplicative. That means it distributes over products of functions. T is a lattice homomorphism. That is it satisfies this commuting with it commutes with taking the absolute value. It's also it's not so important here for now. It's an extreme point of of this set of operators. It's a convex set, and T is an extreme point if and only if it's a lattice homomorphism. And the most important thing is that T is actually a Koopman operator of a continuous function. So if you think of passing here from the dynamic situation to the operator dynamic situation, you don't lose anything. So you can go back and forth. Phi is uniquely determined by T. So there's a one-one. This is an isomorphism of categories. So on the topological side, we're good. Now, how about the measure theoretic side? And here, it's actually not true. So here, actually, it's not the same. So you cannot go back from, if you have, let's say, such a situation, a Markov embedding on an L1 space, it's not always induced by an underlying state space map. And there's an important subclass of probability spaces where that actually is true, and that's due to von Neumann. So the von Neumann theorem is actually the equivalence with 3. And that is involving the notion of a standard probability space, which is modeled on a Polish measure space, like a Polish topological space with probability measure on it. And that's actually, I think that's the reason why, well, one of the reasons why ergodic theorists like standard probability spaces so much. Actually, there is this one-one correspondence between Markov embeddings and underlying state space maps via the Koopman procedure. Actually, we looked in the literature, we were not so convinced about the proofs we could find, so we made up a new one, and I can highly recommend this proof in our book. Good, so that's the point. So when we are on standard probability spaces, then we are good. But now, since we do not want standard probability spaces, the restriction to this, we have to look what we can actually say in general. And here is here's the next point, and that's about models. So that's the next point. So when we start in an abstract situation, then one actually can always find an isomorphic abstract situation which is actually induced by a Koopman operator. So in a sense, modulo isomorphism, the classes are the same. And so this is the next theorem, and I call this the section about models. Here's the theorem. So if you have an abstract measure preserving system, that means you have an L1 space of a probability space, you have a Markov embedding on that space, and you have a subalgebra of L infinity which contains the constants and is an invariant C-star subalgebra of L infinity, then you have the following. You can find a topological system, right? That is a compact topological space, a measure, a continuous map phi, an invariant probability measure on that space, and you can find a Markov embedding of L1 of k to L1 of x that intertwines the Koopman operators and maps C of k onto A. So because it's a Markov embedding, so this is the measure has full support. So okay, C of k really sits as a subspace in L infinity, and phi is then injective. So that's a bijection between C of k and A. The proof is actually very simple if you know the Gelfand-Naimark theorem. Gelfand-Naimark theorem provides you first with a mapping phi on the level of continuous functions, and then you transfer the measure, and then you transfer the operator. Because the operator is multiplicative or lattice homomorphism, you find an underlying dynamics, and then you close everything. So ck is dense in L1, and then you transfer phi, you extend phi by density to L1. So it's actually a straightforward proof if you know the Gelfand-Naimark theorem. The range of phi here is the L1 closure of A. That means if A is L1 dense, if A is dense in L1, that's the case if and only if phi is actually an isomorphism. Good. So this is the important theorem, and our philosophy in our book and also in my subsequent endeavors is actually to use this to reduce measure-preserving systems or the study of measure-preserving systems to the study of topological systems by choosing good subalgebras here and modeling the system on a good space. And I will show you examples for applications now. Okay, so now we have to switch off this again. And so this is now my fourth point. So I want to show you some applications of this theorem, how you can work with this and reduce measure-preserving situation to topological situations. Actually, because of time reasons, I don't want to say my first point was to prove the disintegration theorem in the general case by choosing models and showing that that actually the proof becomes very natural and easy if you choose compact models. But for time reasons, I skip this. I want to talk about joinings first. So what is a joining? Actually, Yuri Tomilov said this is seems to be a difficult notion. Well, sorry, Yuri, I will not offense. But actually, I find it also a difficult notion. So, but when you look at it in the right way, from a functional-analytic point, it becomes also for functional analysts, it becomes a natural notion. That's what I want to tell. So, what is a joining? So, a joining is, suppose you have two systems, one on x1 and on x2, with Kopman operators or with formal Kopman operators. What is a joining? Well, a joining is actually something where you can embed this whole situation in one larger L1 space in such a way. So that means, so here you have embeddings, Markov embeddings. That's the first one. Let's say J2, and that's J1 that map as Markov embeddings into that larger space, and you have commutation of the Kopman operators. That means so maybe I should stick to that notation. So you have J is 1 and 2. So that just means you embed both systems in a larger system. And in such a way that actually this is minimal. That means if you take the range of J1 and the range of J2, then this is actually generating everything. So you cannot find, this is the smallest sub-lattice, closed sublattice that contains these two. So then that means that if you take the lattice, the closed sublattice that contains the range of J1 and the range of J2, then this is actually everything. So if you think of the lattice of factors of a system, that just this means that within the lattice of factors of L1, these two systems, so it's the supremum of these two systems, the smallest factor that contains them both. Okay, now if you have such a joining, oh, by the way, you always have one, namely the direct product. So if you just take x1 tensor, x1 Cartesian product with x2 with a product measure, that is always, and the canonical like embeddings, that's always a joining. Because, okay, so here's an example. So y is x1. time. Obviously, I'm talking to the functional analysts here because the ergodic theorists know this stuff, of course, very well. So if you take this with a product measure, and you take the embedding J1 of F is just F with projection onto the first coordinate, and J2F is F projection onto the second coordinate. So this is a and the dynamics, the product dynamics is adjoining. So this is a standard way of forming a joining. Now, if you have such a joining, then there's an operator, this operator S, which is going from here to here and then taking the adjoint of this operator down. I forgot to say that the adjoint of a such a Markov operator as I defined is also a Markov operator. It works on L infinity first, but then you can extend it. Has the same properties. It preserves one. It preserves the integral. It's positive, and then you can extend it to all of L1. So if you do this, so this is the first one, and then you take the adjoint. This is a Markov operator from purely on the systems that you started with. And actually, there's a theorem that says you can go the other way around. Well, this Markov operator has this property. So this is the one on x1, and this is the one on x2. So if you can compute easily, and then so if you start with such a situation, that means you have a Markov operator from one system to the other that satisfy this this equation, then you can construct a joining, and essentially unique joining, such that this operator becomes this operator. And now this is done easily by choosing topological models. So here is just a sketch of proof. Well, proof, little sketch. How do I do this? By choosing topological models. Well, in the first place, this whole situation is actually categorical, so I don't need base space representations. It's just about operators. So if I pass to an isomorphic situation, I'm still getting such a picture. I mean, I'm just apply an isomorphism, and so without loss of generality, we can assume that the xj are compact. And actually, not just that, the Koopman operators actually leave C xj invariant, and the Markov operator also maps the continuous functions of one space into the other. I mean, the cheapest way to do this is just to take as the subalgebras just the L infinity algebras. Then you get enormous big compact spaces, but at least you can do it. But in certain situations, you can actually take different compact sets here. I mean, you can take smaller subalgebras. The only thing you have to make sure is that the subalgebras that you take are just are invariant under the operators, under the dynamics, and so S maps one into the other. So then of course I'm just taking the compact product space. Now we are in a compact situation that's a compact space, and I'm defining the operator Q as from the continuous functions of the product to the continuous functions of the second factor in the following way. If I have a function of two variables, what I'm doing is I'm fixing the second variable, then it becomes a continuous function of the first one. Then I can apply S, which maps into the continuous functions on the second, and then I can evaluate again in x2. a moment's reflection shows you that this construction, this definition is perfectly well defined, because this again is a function I can evaluate, and this becomes again a continuous function in x2, continuous function in x2. So if I'm looking at elementary tensors here, that like functions that are just of the form f of x1 times g of x2, then if I plug this in, that just means that I'm getting this, s of f times g. Now, this q maps 1 to 1. It's a positive operator. On x2, I have a probability measure. I take the adjoint. I transfer this to this space. So is q prime of mu x2. So mu x2 is the probability measure on x2. This is an operator. Take the adjoint that maps measures to measures by the Ries representation theorem. So this is a probability measure on y. So it's a p measure on y. And now actually we define the embeddings of L1 of x1 into L1 of y by, well, the canonical embeddings. And so on, the same for the other side. And the rest is really like just exercise of computation, that in this way you get a joining, and actually you get that S is really the embedding here and joint of the embedding here. So you get a joining, and it satisfies this this equation. So this is a way of constructing joinings by using topological models. Now, of course, ergodic theorists say, yeah, but why? I mean, when I start with let's say, a standard probability spaces, then I actually would like to model my joining on the product of these two spaces, and not just on some other whatever space. Well, actually, in the case that you are on a standard probability space, you can choose your models in such a way that they are metric. Because okay, you have dense countable sets, and then the generated C-star subalgebras are separable. Now, if you have a CK, which is a separable space, then K, as a compact space, is metrizable. So that means if you choose your subalgebras carefully, then you can arrange it in such a way that these two spaces, compact spaces, are metrizable. So also, the product is metrizable. Now you have a joining modeled on that product, you still have models. But then von Neumann's theorem comes and then says, okay, well, this situation is isomorphic to the original one, so it is induced by base space mappings. So you can transfer everything back to your original product system. So you don't have to mess around with null sets or whatever in Borel category, passing to compact spaces there, and then just invoking von Neumann's theorem. So von Neumann's theorem is then just the universal tool to arrange it in such a way that one doesn't stay on some unknown models, but comes back to the original Polish spaces, let's say, or standard probability spaces. Okay, so this is one application. There's much more to this, because this whole construction can be used also for infinite joinings. I mean, this is just two joinings of two systems, but you can do infinite joinings. And actually, what is called infinite joining in ergodic theory is called dilation in operator theory. So you can, with the same technique, you can construct Markov dilations of Markov operators. And well, this has been done also by Nagel and Palm and so on. Okay, so this was my story about joinings, just to show you that this notion is actually natural, and the technique is helpful. Okay, so here now my last part of the talk, I want to give you a different application. Actually, you will not see proofs here, because they would require a bit more time. But just to show you also an application here where a classical theorem can be the proof of a classical theorem can be considerably simplified. Although I don't show the proof, you will not see how simple it becomes. You have to look into the paper. But just I want to inform you about this. So this is a joint work with Nikita Moriakov. And this is about systems with quasi-discrete spectrum. So in our book, we have the situation of discrete spectrum, and our way to prove the Helmholtz-von Neumann theorem that an ergodic system with discrete spectrum is isomorphic to a group rotation on a compact group, monothetic group. This is done in the following way. So you first you pass to a nice model, a topological model, and then you actually are in the topological discrete spectrum situation where you have all the methods of topology, and then you there it is very easy to see that this is a group rotation, and then because you somehow from the eigenvalues you just construct the group directly, and the homeomorphism then is easy, and then you are there. So it's the idea is also here the measure theoretic situation is a corollary of the topological situation. And so I thought, okay, this should be true with quasi-discrete spectrum systems too. And actually that works in the same way. It's just a bit more complicated to handle these notions. So let me just say, what is this? A system with quasi-discrete spectrum for people who haven't seen it. So suppose you have such a system, and you suppose that it's totally ergodic. That's a technical assumption. One can also say something about non-totally ergodic systems, but I restrict to these. That means just that if you that every operator, that means the fixed spaces are all just the constants. So every power of the operator has just the constants as fixed vectors. That means totally ergodic. So T is ergodic, T square, and so on. Now, define the group G tilde. That's all the L1 functions that have constant modulus 1. That's a group. You can multiply. The inverse is just the multiplication with the adjoint with a conjugated function. And on that group, you consider the homomorphism G tilde to G tilde. That's lambda f is f bar T of f. So actually Tf divided by f, if you like. So this is a group homomorphism of this group. Now the next step is, okay, I'm writing it here. So you define the Gn to be the kernel of lambda n. You have to be a bit patient. You will see in a second where this leads to. So Gn is the kernel of lambda n, and G is just the it's just the union of all these kernels. So on G, it's clear that G is lambda invariant, and actually lambda is nilpotent on G, because in every point is in some Gn, and then for n iterations of lambda, you are to the constant. So this is a nilpotent. So G is lambda is nilpotent on G. Okay, now what has this to do with spectrum and eigenvalues? Well, this is the following. Okay, G0 is obviously just the constant 1 function, because that's the kernel of lambda, it's the kernel of the identity. So that's just 1. But what is G1? Well, G1 is all the constants with modulus, constant functions with constant modulus 1. That's the fixed space of T intersected with G tilde. So why? Because, okay, what is G1? G1 is the kernel of lambda. So when is lambda f equal to 1? Well, that means that Tf is f. So f is in the fixed space. And since we are ergodic situation, it's a constant. So this is G1. But G2 is the f in G tilde such that lambda f is in G1. So lambda f is a constant. So if lambda f is a constant, then Tf is a constant times f. But that means f is an eigenvector, and this constant is an eigenvalue. So this is those lambda in the torus where Tf is lambda f. So there's a lambda in the torus, so Tf is lambda f. So that means, and if I map this, then I'm getting exactly that constant. So this is just the constant functions that have a value their value is an eigenvalue of t, and I embed this into t by let's say eta 1, so lambda 1 is mapped to lambda. This is G2. So this is the group H1, and this is the group of eigenvalues. Okay, now Hn is the image of Gn plus 1, and these are called quasi-eigenvalues for this operator. And now I'm taking the union of all these. Then this is just the image of G under lambda, and I collect this in a triple, which I call a signature, the signature of the system. So this is the group of quasi-eigenvalues. That's this homomorphism lambda, which is nilpotent, and eta 1 is just an embedding of H1 into the torus. This is a signature. Now we say that the system has quasi-discrete spectrum if the linear span of these quasi-eigenvectors, so the linear span of G is full, so it's everything, or it's dense in L2. So X, so this L1xt has quasi-discrete spectrum if the span of G is everything. So in L2, let's say it's in L2. Or in L1, it's then span is in L1 dense. Okay, so now we need another slide here. Hope I can. Let's see. Okay, I have to put this down. This is the wrong one. This is the right one. So, so here is the theorem. And now the point is this theorem is old, but this theorem was first proved by Abramov, but somehow in an awkward way. It was modeled on the proof of the original Helmholtz von Neumann theorem, which to my test is also proved in an awkward way. Okay, whatever. Was also proved in an awkward way, because what von Neumann and Helmholtz did, what they prove is, and what Abramov did, is first he showed that if I have two dynamical systems with quasi-discrete spectrum and their signatures are isomorphic in an obvious way, then the two dynamical systems are isomorphic. And second, he showed that to every signature I have a quasi-discrete spectrum that has this signature as signature. So with every abstract signature, so to speak, I have a concrete dynamical system. And then, of course, that means every dynamical system with quasi-discrete spectrum is isomorphic to such a concrete one. But this is somehow a bit weird. I mean, first you prove everything two are isomorphic, then you need a realization theorem that you can realize every signature, and then you have the representation. So actually, I think it's much more natural to go for the representation directly, and then the isomorphism theorem actually comes for free. Not the realization though, but the isomorphism comes for free. This is the theorem. I know that I have to stop. So just showing you that is the classical theorem that if you have a totally ergodic system, quasi-discrete spectrum, then you can represent it as an affine automorphism system on the dual group of this quasi-eigenvalues. And now this proof, there's also a topological analog, which was proved by Hahn and Perry a couple of years later. And it was proved in the same way. Also first isomorphism theorem, then realization, and then you get the representation as a corollary. So actually, with the notion of topological models, you can do this much easier. So the measure theoretic situation is a complete corollary of the topological one, because you just take this span of G, which is an algebra, because G is a group. So the span of it is an algebra. You take the infinity closure. This is a good C-star subalgebra. You represent it on a compact space as a compact space C of K, and then there you have topological quasi-discrete spectrum because of the total ergodicity here. There it is uniquely ergodic. Of course, you have to work somewhere. In the topological case, you have to work. But my point is, you only have to work once, namely in the topological situation. The measure theoretic situation is then just a corollary. Okay, so I'm about to finish. Just one more word. So this paper will be tomorrow on arXiv. I just submitted it yesterday. We had some last amendments to do. There's also a second section which is completely independent of these representation results, where we also cover in an completely operator-theoretic way the other results of Hahn and Perry about these systems. In particular, like a really straightforward proof that these systems always have zero entropy. Without that, you don't have to put in a lot of knowledge about entropy to see this here. For the future, there are, of course, many more things to say, and so one of the challenging topics are co-cycle extensions and the functional analytic treatment of co-cycle extensions. Up to now, we don't see a Koopman approach to co-cycle extensions, but so this is on the list. Classification of abstract isometric extensions, just for the ergodic theorists here, and then also exploiting the Hilbert module structure in a purely functional analytic way. Actually, there I would like to speak to the experts, because they know maybe more the literature than I do, and maybe many things are already done. But so we will do this in private conversation then. So thank you very much for your attention.